Our main task for this week is to figure out what to do when our code reaches some impossible situation. We saw this example at the end of the previous video. We've actually seen this come up a couple of times in the last few videos, where we have functions that have a certain obligation. So this last function on line 10 is supposed to return a string, and it takes as its input some vector of strings. And the one on line 16 takes a vector of ints and returns an int. And yet there could be a situation where we get to line number 13 in the function defined on line 10, and it turns out the function can't reasonably return anything. It's in an impossible situation. And that is the case where the vector is empty. So on line 10, the function last is supposed to return the last element of the vector. The vector contains a bunch of strings, and so we return a string. And it's expected when I call a function that it uphold its end of the deal. It return a string. But what if the vector is empty? Well, then there really isn't an element, a last element for me to return. So what do I do? And in a sense, this is handling an error case. I mean, we could argue that the caller should have known better. And there are reasonable cases where you can expect that a function should not handle certain errors because the caller should know better. But we need to make that decision ourselves as programmers. We need some option for cases where we do have to handle all of the weird stuff that could come in. So inputs that we're not expecting, including things like passing an empty vector and expecting to get back the last element. So what do we do? The function has to end, it has to return something in the modality that we're familiar with. So what does it return? Well, you could make an argument that we could return a special string for the case where the vector is empty. So we could return the word invalid. We could return an empty string. But the problem is what we're doing there is choosing a sentinel value. And we have no assurance that those sentinel values, like an empty string or the word invalid, aren't legitimate elements of my vector of strings. And so if we return some special string value as a way of signaling that the function failed, then we could be getting ourselves into trouble if it turns out by coincidence that that sentinel value actually is a valid input. And the same thing is true on line 16. On line 16, our job is to return the last element of a vector of ints. So what do we do if the vector is empty? Do we return 0? But 0 could actually be in the vector. So how would the caller know that an error occurred? How would it know that we failed? So we need some way of handling this. And we can think back to what we did in C. So in C, we maybe sometimes used sentinel values where that was appropriate. In some cases, we just bailed out altogether. We just quit the program and said, sorry, I can't continue. And in some cases, we assumed that the caller would be able to sort themselves out. So we allowed the error to occur and just didn't handle it at all inside of our function under the assumption the caller would have to sort out their own problem. We want something more robust. We want the option in C++ of the function being able to handle strange errors that come up, even if we assume they won't usually come up. We want the ability to handle them. We want to handle exceptional cases. So there's a feature I'm going to introduce that'll help us with that. I'm going to introduce it sort of backwards. What I'm going to do is show off that there have been a couple of cases we've already seen where this feature has shown up, and then work backwards from there to see how we can use it in our own functions. I'm going to start with these two examples. I think there's an exercise here. I guess I'll start with this one then. So this program here, it contains a vector with 6 elements. So the indices of the vector go from 0 up to 5. And then it contains some code that asks the user enter an index in the vector, and then it reads the index into this int variable. In the event that an int cannot be read, so you can see this if statement here. So if the user enters words or something instead of an int, then we're able to catch that and say, sorry, you didn't enter an index. If the user enters an int, then I plug it into the .at function and I print out the value at that index. So before I show off the error case, I'm going to show off the case where it runs correctly. So the vector has 6 elements, so indices 0 through 5. Index 0, 1, 2 is the value 116. So if I enter 2 here, it prints out that the element at index 2 is 116. If I enter 4, then it prints out that the element at index 4 is 187. So that seems to be working as expected. If I enter something that is not a number, then it says you did not enter an index because it's unable to read that data into an int variable. Okay, so the error case, the exceptional circumstance is what happens if I enter a number, but it's a number that isn't a valid index? How do I work around that? Before I talk about that, though, let's talk about this other case. So here's a little exercise. This involves using a function that I don't think I've used in a video yet, but you've probably seen in your labs or in a live lecture by now. So this is some code that reads a string from the user and then prints it out as a string, and then the task here is to try and convert it to an int. So if the string contains an actual number, convert it to an int. And so I'll compile the unmodified template before we go any further. So enter a string. Okay, I'll enter the string 187. And okay, so now I have 187, the digits 187 in a string. But I could also enter something that wasn't a number, like the word hello. Okay, so the task here is to find some way of converting this string to a number, if it contains an actual number, if it's the string like 6 or negative 187 or something. And it points out that there is a function in the standard library that does this. I'm going to try and use that. So I'll say int I, I'll make a new int, and then I will set I to be equal to the result of this function s2i. So there are people that read this. I know I've told you already I don't like pronouncing this like a word because there are no vowels. I'm conscious that yes, this does contain vowels, and yet I still pronounce it s2i, string to int. There are people that pronounce this like an actual word. There's no accounting for taste. So I'm going to pass in my string. So the s2i function takes a string as its argument and then returns the result of converting that string to a number, to an int value. Okay, so we'll try running that. I guess we should probably print out. The compiler is making a compelling argument here, which is that I should print that out. As a number, the value is the value of I. And I'm going to try and demonstrate that s2i is indeed actually doing something useful for us here. So I strings and numbers, so I enter the string 187 as before, and it prints it out as a number, the number 187. But I could also enter something just to prove that s2i is doing legitimate work here. What about 000187? So we know that that's just the number 187. If I try parsing this as an int with s2i, sure enough, it comes out as the number 187. So it is turning it into an actual int. It's able to interpret that as an int value. Okay, so what's the exceptional case here? I guess I should do at least one more number. There's the number 6 and maybe the number -1 or something. Okay, so it is parsing. When I enter a number, it's able to parse it. But what about cases where it isn't a number? So the prompt specifically refers to that. Otherwise, print out not a number. So we have to have some way of knowing whether the string we were given, that the user entered, is a number or not. So what do? And that brings us back to the same place we're in with this vector index case, which is we have this vector of 6 things, and the user enters an index. And if all goes well, if they use the program correctly, so in what we think of as the normal use case, if all goes well, then we enter a valid index and print out the element at that index. But what happens if not? So what if I enter something that is a number but isn't a valid index, like the number 100? Press enter and we see this. We've actually seen this message in a previous video, and I pointed out at the time that there's a lot going on here. So what's actually happening here is the C++ runtime system is generating this message. My program isn't doing this directly. This is the result of an error condition arising that wasn't otherwise handled. And ultimately, that is the topic for this week. It is how do we sustainably generate error conditions in our program in such a way that we don't get stuck in impossible situations, but also that in a program where it's appropriate to do so, we can actually handle the error and the program can continue. In this case, my program has not included any logic to handle this error if it occurs. As a result, we get this perfunctory message, and then we get this, which is the program crashing. It is the operating system ending the program in unusual circumstances because it can't reasonably continue. The goal of this week is to talk about how to generate these errors, but also how to handle them safely so that our program can continue. So let's see if we can take this apart. What we have here is std out of range. Interesting, throwing an instance of std out of range. And if we stare at that and acknowledge the word instance there, it sounds a lot like this might be a type. And we also have this, a message that seems to be specific to the situation. We can see there's the number 100, there's 6, the size of the vector, and here's some legalese that sounds a lot like something to do with vectors. We see the word range check, we see the word vector there. All right, let's contrast what happens if I go over here. So in my strings and numbers program, at the moment, I read a string from the user, and then I attempt to convert it to an int. And let's take a moment to reflect on exactly what s2i is supposed to do if the string is not a number. So what is it supposed to do? If I pass in a string that contains the digits 100, it'll return the number 100. If I pass in a string that contains the word hello, what is it supposed to return? It's supposed to return an int. It can't return anything else. If it returns 0, because you could argue that 0 is a good default fallback value for an int, if s2i returns 0, we might think that the user entered a string which was actually the number 0, which isn't the case. So we need some way of s2i being able to get out of that impossible situation. So let's see what happens if we do that. Okay, if I enter the string with the number 0, then it converts to the integer 0. And that's not that surprising. If I enter the string with the word hello, then I get this. And you'll notice this looks pretty familiar. So although the message down here looks a little bit more Spartan, I mean, all it's saying is s2i, we notice this. Terminate called after throwing an instance of this thing, std invalid argument. So in the previous case, maybe we'll run them both next to each other. So when I enter the index 100 here, terminate is called after throwing an instance of out of range. And I suppose out of range is fitting because I gave an index that wasn't in the range of the vector. Invalid argument is also sort of fitting because I passed into s2i something that it could not handle. s2i was expecting a string with digits, but I gave it a string with something else. And so it, I guess, engaged in what we call throwing, whatever that's supposed to mean, an instance of this. And so if we stare at this for a minute, maybe it's not completely obvious, but it turns out that this in std invalid argument and this std out of range are actually types. They are objects. And these functions, as a way of getting out of that impossible situation, they are providing us in unusual circumstances with these special objects, these special error objects. We call these exception objects, which is a way of the function sort of sending up a flare and saying, I'm sorry, I can't do my job, I have failed. Here is some object that can give you an explanation of what happened and maybe provide you a way of fixing it. And so we call this process of generating these errors, these exceptions, we call it throwing an error. And I'll talk more about that in the next video and the one after that. But what we need now is the ability to, well, first, how do our functions get that facility? But also, actually, I think it's fitting when we're staring at these two examples, how can we handle the problem? So an example is the s2i function in this program here is in an impossible situation. We tried to convert our string to a number, but we couldn't. But on the other hand, that doesn't mean all is lost. Maybe my program can continue, and in fact, the prompt seems to imply that it should. If the string does contain a number, print it out. Otherwise, print that the string wasn't a number. So if that error occurs, the program is supposed to handle the error gracefully. It's supposed to actually do something. And so we now see that the function does apparently have some exit strategy if it's unable to do its job. The question now is, how do we catch that and handle that problem without the program ending, without it having to crash like it's doing here? By the same token, we could argue that we could do something similar here. Now, I know you might be staring at the vector example and thinking, well, I could just check before I use the index that the index is valid. I could proactively handle the error, and that is true. In general, that's probably the way I would handle a situation like this. But an alternative would be, we've put .at, the .at function, in an impossible situation. An alternative would be to just do that, to throw out an index it can't work with, and then handle the error when it shows up, this error called out of range. And so we actually have, we have either option there, but for this program, we only really have one. We have no way of determining in advance whether the string really is a number or not. The real judge of that is the s2i function. So I guess our only option is to give the s2i function our string and just hope for the best, and then hopefully handle that error if it occurs. And to do that, when the functions generate these errors, we call it throwing an error. And it turns out just like a function can throw an error, we, the caller of the function, can choose to catch it. We could, if we know that we're in a situation where the function may fail, where an error may occur, we can choose to set up a way for our program to handle that error. And it's called catching the error. And that is a two-part process. It involves first having to give the compiler an advance warning that you might need to catch an error. That is, that you're about to attempt something that might fail. And so we do that by wrapping our code up into a block. So I'll just indent the code here. We wrap the code up into a block called a try block. What I'm doing here is telling the compiler, I want to try doing this. So the operative word is try. I might fail. And in the event that I fail, during this block, some error condition might arise. And again, we call that formally an exception. In particular, it could happen here. The call to s2i might fail. You've noticed that when s2i fails, it throws an instance of this type. And I'm allowed to tell the compiler when I try something that if something goes wrong, it might need to catch a particular type of thing. So in this case, I'm going to catch an instance of invalid argument if it arises. And this is called a catch block. Now, the next few videos are going to unpack this in great detail. So for now, we're just seeing the infrastructure as it forms. I'm not going to worry too much about the specifics of this syntax right now. And so I suppose what I want to do is I want to try to convert the user's string to a number. If at any time that fails, so in particular if S2I can't do its job, then I want to catch that error. I don't want the program to end. I want to be able to handle it myself. And so what we typically do is create a try block with a bunch of associated catch blocks. And they go hand in hand. Just like if and else, we have try and catch. We'll see later that we can have more than one catch associated with a given try. The catch block can only handle errors that occur during the associated try block. And so in this case, I will say, I suppose the prompt was, in the event that the string cannot be converted to a number, print out not a number. So I'll do that. And then we'll try running this modified version. And as before, I'll type in the string 187, it gets recognized as a number. I'll type in the string 0006, that gets recognized as a number. And now I'll try typing in a string that isn't a number. And we can see it just prints not a number. The program is able to end on its own terms. And just to prove that, I'm going to print the word done down here. I'm going to prove that the program is reaching the end of main. Whereas before, the program was ending immediately as soon as that error was generated. We never got to the print statement after the error. Because when the error condition arises, if nobody handles it, then there's nothing to be done. The program just has to bail. Whereas here, we have an option. We have some path we can take if the error occurs. We have some graceful way of handling the error. So I'll try this again. I'll just enter the word hello, and we can see it gets to the word done. So main does end. Even though the error condition arises here, main does reach the end. And it does so because we're able to catch that invalid argument object that is thrown by S2I. Now, you'll notice the way I've named this here, it looks a lot like a function signature. And that's because, as I'll show in the next example, the object that gets thrown back might be more use than just knowing its type. We might actually want to inspect that object and ask about what's happening inside of it. That might give us a clue as to what the error was or how to fix it. So the next few videos we'll talk about that in detail as well. One note before I continue, though, you'll notice that I caught this value by reference. And again, the specifics of what this means we'll unpack later, but I will show what happens if I get rid of this ampersand. And we get an interesting bit of foreshadowing. It says, catching polymorphic type by value. Well, we'll see what that word means in a few weeks. Certainly, it's something that catches our eye. But the remedy for now is when we work with these standard exceptions, so invalid argument or STD out of range, make sure that you catch them by reference. And there it is. So we are back to the state we were in before. We're catching the exception and printing out not a number. That brings us to this. So this expression here, so that this function call, the call to .at, it may fail because it could be that there actually is no element at that index. I could provide an index that's invalid. As I mentioned a minute ago, this is a case where you could handle the error proactively. You could just check that the index is valid before using it. And arguably, that is probably a better path. If you can handle errors proactively, in general, it's often a good idea to do so. You should only use try and catch to handle error conditions that you don't expect to happen, that are not a normal case. But I'll try that here because we are allowed to use that. We saw that the .at function generated a particular error. I'll just reproduce it here. If I enter the index 100, we get the error std out of range. Okay, so I'll try catching that. So first I'll wrap up the place where the error occurs into a try block. And of course, I can put a try block wherever I want in my program. A try block is scoped. And that means that if I create a variable inside the try block and then use it, the use has to occur inside the same block, because once the try block ends, for one reason or another, all of its variables that are created inside the block get destroyed, just like any other scope. In this try block, I'm going to catch, if it occurs, an instance of std out of range. We'll call that E again. And so we know that the .at function can throw an instance of out of range. What I'm telling the compiler here is I would like to try to run this code, and in the event that an out of range exception is generated, I would like to catch it. And so I will write here, not a valid index. And then we'll just scroll up until the last time I compiled this other program, which might be longer ago than I thought. So I'll try the index 4 again, that's 187, and now I'll try index 100. And it says not a valid index. And you can see again, the program is now finishing, it's terminating on its own terms. We're not seeing that the program crashes. One thing I hope that you might have noticed and deduced about the behavior of try and catch, without me having to tell you, but I'll tell you anyway, is that once the error condition arises, the try block immediately terminates. So you'll notice line 17 tries to print some output, and yet when I entered an invalid input, the element at index, this stuff here, never got printed. And the same thing was true in my strings and numbers. Notice that after I try to convert my string to a number, I print out as a number. But yet when I ran the program, so we'll run it again, if I enter a string that isn't a number, it just prints out not a number. It goes immediately down here. And this is one of the characteristic behaviors of try blocks. As soon as the error condition arises, the try block immediately ends. So if during this function call the error condition arises, we immediately jump into this catch block. The entire remainder of the try block is skipped. The scope of the try block ends, and we jump into the catch block. So that means that obviously, once our function has failed, we can't do the rest of the try block anyway, and so it makes sense that we immediately bail out. And the same thing happens here. If .at can't do its job and raises an error condition, we immediately jump into the catch block. We do not attempt to execute any more, not one more line of our try block gets executed. Okay, so there's one last thing I want to point out before we go to the next video, where we're going to talk about actually throwing these exception objects. And that is, what exactly is this? So I've obviously indicated that I want to try to execute this, and in the event that an out-of-range exception gets thrown in the meantime, I want to catch it. If I don't catch it, then the program will crash, because if nobody catches the exception, then it makes its way all the way back to the runtime system, which then by default ends the program. I'm going to talk more about that in a future video. So when I catch the exception, I might want to know more about it. So the .at function failed. When it failed, it generated this object of type out of range. But it might have included in the object some information that I can use. Now in a future video, we'll talk about how we can package up our own information, but I want to illustrate for now that when you catch something, you can give it a name. Traditionally, we give it names like E or EX, just like how we often call our integers I. The exception object E is of type std out of range. And it turns out that these standard exception objects in the standard library have a function that will tell you whatever message has been built in. So the .at function, when it threw the exception, built in a little error message into the object E. And if I want, I can take a look at that. There's this function e.what, and e.what returns to you the string that is the error message. So I'll just print that out. And we'll notice something familiar. Okay, so we'll try index 4 again. That looks good. And now we'll try index 100. And notice the message that I print out that's stored inside the exception object is that cryptic message that we saw earlier. So this is the .at function trying to explain itself, trying to give some explanation, a concise but not very easy to read, a concise explanation of why it failed. And the explanation appears to be basically that the number you gave me, which was the number 100, is greater than or equal to the size of the vector. Now, we're not going to think too much about what the word this is supposed to mean until a bit later in the course, but the size of the vector is 6, and of course that means the last valid index is 5. Any index that's greater than or equal to 6 is therefore invalid. And so the .at function created this error object and then threw it as a way of indicating it couldn't complete its job normally. We then caught the error object, and that not only gave us the ability to handle the error gracefully, but we're able to use that error object and obtain maybe more information about what went wrong. And in a future video, when we are writing the code that both throws and catches things, we will notice that the catch semantic of being able to use the error object is actually quite useful. But in the meantime, we first have to learn how to write code that can throw exception objects.